After watching the manufacturing process of giant steel beams, I finally understand why steel beams are considered one of the greatest inventions in the field of infrastructure today. A seemingly inconspicuous I-beam requires consideration of bending moments and compressive loads, increasing the load-bearing strength by tens of times to address issues such as bridge collapses and building collapses. Here is a local large-scale steelmaking factory, which is the first step in producing I-beams. First, scrap metal transported from various places is uniformly placed in the sorting workshop. The factory receives more than 200 cars of various scrap iron daily to meet the massive consumption in the steelmaking process. The scrap metal is hoisted to the transfer furnace, which provides all the raw materials needed for the steel beams. Although this iron barrel may not look significant, it can hold up to 110 tons of scrap metal. The considerable furnace door slowly opens, and the 1,600-degree molten iron instantly illuminates the entire plant. Now, the scrap metal is poured in. When the metal meets the molten iron, combustion of over 3 meters high erupts around, which is the first step of metal smelting. Due to the high temperature, workers must wear flame retardant and heat-insulating suits daily to reduce the risk of burns. We move on to the crucial step of electric arc furnace smelting. The electric arc furnace releases electric energy into the furnace through graphite electrodes, converting electrical energy into heat energy and then using it as a heat source for steelmaking. This type of steelmaking is large-scale and often seen in large steel plants. As the smelting is completed, the molten iron pours down. The temperature is over 1,700 degrees Celsius at this time, making it only safe to watch from afar. Workers fully equipped start directing transportation. We move on to the next step of removing impurities. Because scrap iron is often mixed with many other metals and impurities during the smelting process, failure to remove them will damage the quality of the steel structure. Only by adding an appropriate amount of slagging agent can the purity of the molten iron be ensured. However, one refining step is not enough more than H for the 140 tons needed. Close the furnace door to prepare for secondary refining. This step can make the molten iron purer and effectively increase the stability factor in the subsequent casting process. After several tens of minutes, the refining of the molten iron is completed, and it is ready to move on to the next step of casting. Because over 100 tons of molten iron are stored inside, extreme caution is needed during transportation. Next, workers clean the transfer nozzle. This component transfers molten iron, making it flow into the lower part more quickly. This is an ingenious design. After all the processes are ready, we will enter the casting stage. When the molten iron flows in, the equipment will produce a certain amount of vibration to increase the flow rate and facilitate the formation of the steel structure. Let's take a look at the semi-finished steel beams. At this time, the temperature is approximately 900 to 1,000 degrees Celsius. They are cut while hot and segmented according to specified dimensions. From the footage, the shape resembles a steel rail, with the only difference being that these need to be marked for batch and model identification. Then, they continue for secondary heating, making them easier to shape in the subsequent rolling process. The furnace door is closed, and the equipment's I-beams are continuously heated for 2 hours, gradually raising the temperature to 1,270 degrees Celsius, which is a rather time-consuming process. The heating is completed in the blink of an eye, and multiple sets of rollers push them to the next step. The formal rolling begins. The machine shapes the steel by rolling and squeezing. This process must be repeated dozens of times. Considered the first rolling. Let's look at the effect of the first rolling. Compared to the initial volume, it seems smaller. It enters the second round of precision rolling. This high-temperature steel beam will be rolled 10 times in the equipment ahead, the 10 separate devices in the footage. Each rolling round is followed by one cycle until all 10 cycles are completed. After that, it's time for cooling. The densely covered cooling liquid is continuously sprayed onto the surface. The spraying varies depending on the quality of the steel structure. They are transported forward to cool naturally, which usually takes about 1 to 2 hours, slowly inching forward. Let's take a closer look at the details. The thickness has decreased several times compared to the initial state, while the length has increased several times. Then, they undergo secondary rolling, straightening the angles on both sides, making them resemble I-beams even more. Next is the cutting and segmenting process. The first step is to remove the excess on both sides, leaving only the relatively neat middle part. After several rounds of cooling, the steel beams have returned to room temperature. They are then stacked in groups of 4 and tightly wrapped with equipment. At this point, a complete set of I-beams is formed. Let's take a look at the final product. The edges are neat, and the overall appearance is very orderly. What do you think of this manufacturing technique?